Welcome to the next talk at Alum at Alma. Um, Today we are going to discuss about compilers and industry. And today's speaker is Madhur Amilkanthwar. He is a senior software engineer at NVIDIA. He graduated from IITM with an MS and was advised by Dr. Shankar Balchandran. He joined NVIDIA after graduating from here in the PTX compiler group, which is the assembly language um, for CUDA. And let me just read. Me add multiple people. Yeah. So at the PTS compiler group, Madhur contributed to several key features and drove a complicated set of components meant for customers. He also worked with the Nirvana group at Intel as a key compiler engineer to drive core compiler development for the MLSIC building for training workloads. He made significant contributions to the overall compiler and also received the important department recognition award. Further, he worked with AMD in the ROCm compiler group to mature and lead any to the key compiler support for AMD GPUs, which we currently know as HIP software stack. The contributions were aimed towards facilitating AMD's compiler to be adopted suitably for performance objectives. He recently restarted his stint at NVIDIA again and is with the Grace Superchip compiler team. He has spent most of his work life in and around LLVM infrastructure. He has published papers in ICS, GPGPU, and PPOP. His work on uncoalesced access pattern detection received a silver medal in the student research competition held at ICS. He has also served as a program committee member on the LLVM HPC workshop co-located with the Supercomputing Conference last year and this year. He has also been a collaborator. The GPGPU paper is with me and one of our former MTech students, Srinivas. So without further ado, welcome Madhur, and thanks a lot for accepting our invite. Over to you to listen to the interesting talk.
Yeah, thanks, Rupesh. Thanks for the introduction, and it's always great to be back and talk to the people or resemble to where I used to be a decade ago. So it's always a enchanting experience to come back to come back to our roots. So let me just share my screen. I'm new to Google Meet, so I may mess up few things. Okay, I started. Can you guys see?
Yeah, the slides are visible. In the presentation.
Yes, it should be visible now.
Yeah, the slides are visible, but it's not in the presentation mode yet, Madhur. Okay, great. Also,
Okay.
yeah.
Okay. So as Rupesh said, he has given a detailed introduction of me, so I won't go over the slide again. But overall, what I would like to say is that uh, so given when Rupesh asked me, would you like to talk to people and share your experiences? Then I asked myself, what do I want to talk to these guys? I mean, the BTechs and MTechs who are just willing to come out and venture into the new academics or go into the industry. Then it was an interesting opportunity for me. But rather than talking into the deep technical stuff, I thought I'll share my compiler experiences and also create some sort of interest amongst you guys to basically introduce this field. Right? During our memtech and during our course, we take compiler classes, but At some point we fail to realize that this is not, this is the book what you introduce, or the book that you read is not, is not just till the last page. The adoption of the compilers, adoption of the technology stack, how companies like NVIDIA, AMD, Intel, Google, Microsoft, Qualcomm, how do they use these compilers? Is that something I wanted to share with you guys? So, although I don't have many slides on the other companies, I have focused mostly on NVIDIA. But towards the end of the talk, if you ask me focus questions, or if you are, if there is enough interest, then I can share you the other companies also, because the reason I didn't want include the details about them is because things change very rapidly in these companies, and I didn't want to go deep inside and take the credit for what they are doing. So I'll be mostly focused on NVIDIA stack and NVIDIA's compilers, but we will be able to relate them to what other companies are doing, and I'll also lay out the ground for that. And the next important point is, let us be this an interactive discussion. We'll take the questions and the end at the end, but if there is something you want to ask then and there, then please don't shy away from asking. So it will be more helpful if you have a two-way discussion, rather than me just talking and you just listening. So just feel free to ask questions. And the next thing that I would highlight is, uh, again, probably the same thing again I'm repeating, but compilers, how they offer interesting computer science problem, how today's industry solve them and all that. We'll mostly focus on that, but we will not go deep in that, because in the spirit of time, it doesn't make any sense to go deep inside every problem and talk about what the state of the art is, how the problem is originated and all that. So I'll give you the kind of a breadth first overview of the compilers. And with that note, let us begin. Uh, So, first of all, this is not a marketing presentation. It is just a, this is being a developer from last 10 years. I'm just talking to you uh, as a developer. So I won't go into the why why you should use NVIDIA technology and all that. I'll just talk about how, as a MTech or a BTech guy, that is that can be interesting for you to pursue the future. So it is not a deep introduction or not a marketing presentation, but it should be enough to get you started. Okay, so I'll start with LLVM. Uh, so LLVM is now, uh, so I don't know how many of you have taken the course or how many of you are aware of compilers, but I will assume that you don't know LLVM. So that basic assumption is something that I will build my foundation on, because that will help people who are not from compiler background to also listen and we get interested in it. So I'll start with that premise. So I'll start with LLVM. Okay, so when we talk about compilers in general, what is a compiler? A compiler in a bare minimum language, or a layman's term, is that it is a software which takes high level programming languages like C, C++, Java, C Sharp, whatever you can think of, and that that software component converts that into the machine language, the language which the machine can understand, right? The ultimate binary that uh, we all talk about. So it's all about that software component, and it's all about, when we say compiler, that is the software component we talk about. But the devil is in the details, right? I mean, the compiler is particular software component is not easy. That okay, you take the line, convert into the binary representation, and then you are done with it. It is not like order of one translator, and internally it does a lot of complicated stuff. It does a lot of lot of things which basically to get you the logically equivalent program that you have written. So that is basically the compiler, right? Now, historically, if you go rewind yourself to 1970s or 1980s, until today, the GNU compiler connection, the GCC, is what everybody uses, right? GCC, G++. It's something that all of us use as a first compiler that we like probably exposed to the first Hello World C program that we wrote. So everybody uses GCC, used GCC or G++ to compile our program. Uh, so GCC is there. I mean, GCC has been widely used, widely adopted in the uh, Linux distributions and in the different channels and different ways in which a compiler can be used. Like, because till 2000 or early or during that decade, early decade of that 2000 to 2010, GCC was the most or probably the only choice for the application developers, right? But when in 2007 LLVM was introduced. Now, LLVM stands for low level virtual machine. The long form probably doesn't make any sense, but this is how it is. I mean, the long form doesn't say it is a compiler, but it's an infrastructure rather than saying it's a compiler. So, so this particular idea or the concept came in. Uh, I should just switch to the new slide. Yeah. So this particular idea and the concept came in master's thesis by Chris Latner. So he was a MS student at Urbana-Champaign, and he advised by Vikram Adve. And during his thesis, he proposed this idea. Now, most interestingly, this idea was proposed in the GCC conference first. Uh, like in one of the GCC quadrants, this idea was there. He proposed that idea, but uh, something happened, and then eventually Chris Lackner decided that it will be a different project altogether, and that is how LLVM was basically started or incubated. We can say that. Uh, but when you look at the first paper of LLVM, where the entire thing began, it was mostly from a point of view of a, a lifeline program analysis and a transformation available. Like, the motivation was to provide you a framework to transform your program or do any optimization or do any kind of a program analysis you may want to do on that. And then grow slowly it evolved in a infrastructure. So we'll go into deep on that throughout the slides. But but what striked out from GCC during that time was the modularity. GCC was not known to be modular, or over the years it has become well modular now. But we are talking about that era where uh, LLVM was just introduced, and the new compiler infrastructure what people were talking about and people were interested in, and the one infrastructure where it aims to adopt the modern programming standards or modern way of development, software development. So that era where LLVM was just being discussed in the conferences and the communities. The one of the important things that what we say is as a unique selling point of this software or this LLVM infrastructure was the modularity. Like, uh, it always aimed to be modular, so that when you want to write a new pass or when you want to write a new functionality in your compiler, uh, it offered a composable components. Like, you can take a small pass and put it in an in a existing ecosystem, and then it should just work out of the box. So that was the main goal of, or that was the main thing that people like, and that people uh, that grabbed the attention basically, and that is where it all started. And then gradually until I think till 2016 or something, it was still a CPU based compiler, but then slowly GPU and all non CPU based platforms also started joining, because the infrastructure is there. And in the next slides I will help to understand how it is more scalable. So so uh, so as I'm saying about the modularity during the GCC time frame, the paper also talks about, how n front ends and n back ends is not a scalable architecture, right? So what do I mean by n front ends and n back ends is that the way GCC was designed, and again we are talking about this 2000 1990s to 2000, that time frame. The way GCC was designed, that it was not thought from a scalability point of view. Like we and it is not a something that you can even imagine, right? I mean, today you may not imagine what kind of architectures or what kind of needs you may have 20 years down the line. So similarly, rewinding to 20 years back, GCC was not that matured enough, or what we can call it as an infrastructure which can be scalable to the any architecture that you may want. So what the software had was like n n languages, if you want to compare, like n, you can say C, C++, Fortran, or COBOL at that point, or even the new languages like C Sharp and all that. Those, if you want to compile to the particular architecture like x86, R64, NVPTX, or anything that you can think of today, at that point, if you wanted to do that, then you would have this end-to-end mapping, like in one language, take that to a particular architecture, and then another language similarly to the same architecture. So it's an n cross n mapping in the software. Logically, of course, you can take that to a common place, and then continue the optimization, or continue to target the particular architecture. Logically you can do that, but in the software or in the implementation, that was not really easy, or that was not really practically possible to do. And that is where LLVM uh, forced its selling point. That is how it organized itself, that futuristically speaking, if I want to target any language from to any new architecture that may come up in future, how do I want to organize that? That scalability and that vision was there in the paper. And you can read that 2007 paper, or 2002 sorry 2002 thesis by Chris Latner. I have given the references to it, but there will be more to it what I am trying to explain here. But the idea is that you have this n front ends, now a single middle end, and a n back ends, and that is how you achieve the scalability that the future may want. And then slowly, of course, the paper is no just talks about the initial idea and the initial implementation. But if you okay, fast forward to 2023, then this particular architecture has evolved into so many things. Like it has built now an ecosystem of the tools and the compilers, and you have so many tools around it, like debuggers, sanitizers, profilers, which uses the same fundamentals, uses the same core at its bare minimum level, and then builds tools around it. But we will focus on the most core part, because that is the most interesting thing for us. So now when we talk about LLVM, you must have heard of Clang, or you will hear Clang as the common go-to tool for compilation. Like now, when we are again relating to GCC, we say that GCC is equivalent to Clang. Now GCC is a driver basically. It takes your program, it compiles it, it calls the enough components to do the optimization, and then finally it calls mm, uh, the code emitter, which basically generate the assembler, and then the assembler sorry it emits the assembly, and then assembler gets invoked, and finally the linker and all that. So GCC helps you to get your program from the first step to till the last step. And now if you want to replace the GCC in the from the LLVM infrastructure, it is going to be the Clang or Clang++. So that is the binary, or that is the tool that you are going to invoke. And inside that, so rather than we are saying that as a Clang, inside that front end, or the first steps that the client takes, it what it does is it uh, lexes and passes your program to build an AST. AST is nothing but abstract syntax tree. Now Here the books will be helpful. Here the books will give you the enough understanding of what is an abstract syntax tree, how do you represent the computation of how do you represent the computation given in a program in a manner which is amenable to the program transformations and amenable to do the classic optimization or classic computer science technologies we have developed over the last so many things, like for example, if you want, after all it's a tree, right? I mean, the name says it's a abstract syntax tree, so it's a tree. So now all your tree and graph algorithms can also be imposed used on this, like for example, say I want to merge two trees, or I want to optimize two trees, I want to prune some children of those trees. So all those techniques can now be used on this abstract syntax tree, because now we have boiled down the computation or boiled down the textual representation of our program into a tree. And that tree is now something that our computer science technologies can understand. So this is where our books can help us to understand more about that. So but now when it comes to implementation, then Clang has already have a huge APIs or huge libraries or huge modules implemented to manipulate these ASTs, reason about these ASTs, and all that. So it's no longer interesting from a development point of view, and similarly uh, from an industry point of view, it doesn't grab that much attention, because it is done and dusted problem, right? Probably it was interesting 30 years back, where, oh, that okay, you have a textual program now, and now you have given me AST, so let me play with it. Now that was the mindset of the researchers, but now it is, we have gone past that. Now it is there. So in the industry, we don't uh, uh, touch this particular component unless we are proposing a new language, right? For example, suppose if you tell me that I want to I want to have a similar kind of a support for a functional programming languages like Haskell in Clang. Although there is a support, but for a time being, let's assume that you as a BTech or MTech guy, you want to take Haskell and compile it or use Clang as an infrastructure to compile it to AST. Then that is where you will have to talk about AST, or you will have to touch this particular source code. But when we are talking about C++ languages, the standards evolve 3 years every 3 years in time, right? C++ 11, 14, 17, 20, that way. So not much dynamics or not much things happen in that area. So this is where the things just start get interesting, but not yet interesting yet. All right. So the front end basically does all this AST manipulation, and then eventually emits the something called as LLVM IR. Now IR means the intermediate representation, which is nothing but a textual representation or a binary representation of your same AST. The AST, initially you had a high level program, you compile it to AST. Now you are serializing that AST to something linear representation of the program. But why does that exist? Why do you need a IR? Now IR is nothing but a language independent representation of your program. You when you are coming from now again recall that we are talking about a common middle end, right? The middle end which needs to understand all the languages. So you need a common language where you can all translate all your languages together, right? I mean, if it is coming from C++ or Fortran, if you can represent that in a common canonical fashion, like add instruction, subtract instruction, then your later part of your software can understand that and reason about that. So that is the one of the many purposes why you need an intermediate representation. So if you are coming from a compiler background to this talk, then I don't need to explain you why IR explain why IR exists. But if you are not from a compiler background, then I think this should be enough to convince you that okay, why I need intermediate representation. The purpose is that you get to a common language from all these n languages, so that the next components can understand and reason about that. That is the one of the purposes of IR. So the job of the front end, the Clang front end, what we are talking about, is to emit that IR, doing the complicated analysis on walking over the EST and all that. So at this point we have the IR, right? The IR, which is a simple file, or or a binary representation of that program, where a middle end can digest. Now the middle end is again a one portion in your compiler which does the optimization on that IR, right? So now what kind of optimizations can be, like, suppose you have written a subsequent adds, like, uh, say a plus 1, a plus 1, a plus 1, so you have written several times. Then this particular portion can just squeeze all those computations and get you to the a plus n instruction, or a plus n computation, which you can do in a single add instruction, right? Now, that is a very basic case, but middle end does a lot of, in today's world, if you come, then middle end does a lot of complicated compiler optimizations, like, to name few: common sub expression elimination, global value numbering, then loop invariant. When you go to the loop, you go like, loop is the one place in any application where software spend most of their time, right? Because you do certain kind of computations again and again, and you may do it n square times, or order of n times, or something like that, right? So that is the most area in middle end where compilers have, or the researchers have spent a lot of their time in optimizing that particular loop. So loop related transformation is something that middle end is expert in doing, and it or the core of middle end goes in that portion, right? So LICM is loop invariant code motion. What it does is, suppose you have a loop and you are just reading from some memory, or say you are just doing a computation which is not going to change again and again in the loop, right? It's the same computation you are doing in the loop. Then compilers, then middle end is smart enough to pull that particular computation out of the loop, right? Because it can reason about that computation and say that, oh, it is not going to change during the iteration of my loop, so let me just pull it out, right? So what do you gain by that is, you don't compute it again and again, so you don't waste your cycles, and you don't waste your energy, and you don't waste your time eventually, right? So that is how you save, or get benefit from this transformation. And that is why we aim to do the optimizations on a loop based applications, or loop based regions of the code. um, so so another interesting example is inliner, right? So suppose, now if you are from a physics background by any chance, then may have been exposed to this uh, weather simulation applications, or uh, n-body simulations, all those things. I'm not expert in physics applications, but what I heard is that these applications are complex in their nature, right? And often they get so big over the time that they get split over the multiple files, or get split over multiple modules in that regard, right? The organization that it happens, that one particular module talks to another, and then eventually you see the simulation getting happening. Now in those kind of applications where the things are split across multiple modules, uh, inlining becomes an interesting choice, because inlining basically means that if a one function calls another function in your C or C++ program, then then you have this branch instruction, or you call that particular function, get the job done, and return back, right? But what inlining tries to do is that that particular function, or the callee of that particular caller, want to inline into that, so that you avoid that the cost of branch instruction, and then returning back from that function. So thus, if A calls B, then with after inlining, B becomes body of A, so that you don't go to the B and come back, right? So inlining is again another area where Middleland spends a lot of time. And you may you may also you may already have anticipated that this inlining is not a easy business, because firstly, how, when, and how do you inline, right? What is the basis of inlining? If your callee of the, or the function you are calling is a small, then you don't want to inline, because uh, if the function is small, then you do want to inline, because the the cost that you are paying is very high. Rather you don't jump to that in the function and come back. You just take that body and call it here, right? If it is a small enough function, then you do that. But it is not just there, right? So there are a lot of heuristics and a lot of analysis happens when it comes to the inlining one function into another. So uh, it looks easy for small applications, but it is not when it goes to the multiple and bigger applications. Um, yeah, so I think that should be more, or that should be enough about the in a middle end. Although this doesn't cover. And yeah, one another thing that I wanted to also talk about is uh, SSA forms, right? Mm, SSA stands for static single assignment. SSC is again coming from research. It is also came from one of the papers, which basically talks about static single assignment, uh, and it is one of the or whatever I say is a mm, one of the things that benefits our analysis. So before, like you can ask that, is SSA important for compiler? Or okay, let me first explain what is SSA. So SSA stands for static single assignment. It is a way of representing your program in a slightly different manner than usually what you represent. So suppose I have a if condition and I have a else condition, and say I'm using the value after if and else condition in my program, right? And say in the if block I have a equal to 2, and in the else block I have a equal to 5, right? So when I go to the IR, or the intermediate representation, I will see this a or the immediate replica of the A, or what we call as a representation of A in the IR world being getting defined or getting assigned two times, right? So in the IR world, you will see that A is getting assigned in if, and A is getting assigned in else same times. So this redefinition, or the definition of a same value in both if and else is slightly complicated for the existing analysis. So what SSA says that I will rename the A in F as A1, and A in else as A2. Basically, it is just the same variable, but we are creating a different copies of the same value. So one value, rather than getting defining it again and again, and reasoning about that, and complicating all the things around that, SSA tries to redefine the same, or renumber the value, or create a different copy of that value again, and in the different places where it gets defined, and using that properly is all about the SSA, right? This is a very high introduction. Again, there is a paper about SSA, and you can look at that. But SSA was another phenomenal, or a seminal milestone in the compilers, where uh, the usual representation of the programs uh, changed, and the transformation or the analysis around that also learned how the SSA can help you. So if you look at the Dragon book or the Muchnik book, they do have SSA based optimizations, but they also have non-SSA based optimization. So if you are reading those books, or if you are reading those chapters, then you will realize that how non-SSA based transformations are so complicated, and how SSA based transformations can simplify the steps. So so now again, coming back to LLVM is strictly SSA based compiler, where right from the beginning you have SSA in your stack, and all the optimizations that use SSA. So this is where again I can relate to that uh, uh, what came from the academic papers became a normal standard in the industry, and how that just got absorbed, and how the further optimization just tuned itself to that particular standard, right? So if you are uh, coming from compiler background, then you will realize that why and how SSA is now used in LLM. Uh, so so now we are going to backend, but before going to that, let us just set the premise let us just set the premise for middle end. What middle end uh, what middle end did for us in this slide is that it optimized the intermediate representation for us. It gave us the most optimal program or most representation IR for us, and uh, which is supposedly the which supposedly takes the minimum number of cycles for our computation. Now, right now it hands over that program to backend, and what backend does is now its job is to translate that program into the machine language, or the final language, or the machine, or the binary that finally can get executed on that. And so I will restrict myself to go into the deeper backend details, but uh, one line I would say is that this is where most of the interesting stuff happens, and this is where your register allocation happens, right? Because till this point, whatever the registers, or whatever the caches, or whatever the resources we have in our machine, we have not assigned that to any of the computation, or any of the instruction. Because ultimately, if you look at a simple subtraction instruction, it is going to take two values and subtract and put it value in a different memory location or memory register. But someone has to do this allocation, and someone has to say that, okay, look at this value, read from these two registers, and read from and do the subtraction, and then finally put the value in that register, right? So that resource allocation needs to be done by someone, and that someone is primarily the backend. But it is not limited to that. When it talks about backend, it has to do a lot of complicated stuff also, because in order to get to that resource allocation, it has to do a lot of lowering. It has to do a lot of post processing. It has to do a lot of legalization, right? Because, for example, suppose you have a subtraction in your program, but there is no subtraction in the architecture available. There is no unit to do the subtraction. Then how do you do that for that particular architecture? So that all lowering and all that happens in this particular component, and eventually you get the binary. And now, in addition to that, it also does the scheduling, because the scheduling is something which helps you to minimize the number of cycles you will take, your program will take, right? Because if a one value is getting computed, and if the another operation is depending on that value, then you don't want to stall. You don't want to wait for that computation to happen. You can schedule independent computations in between that wait cycle. So that is the job of linear scheduling. And this is again coming back to the old papers. So linear scan came from Georgia Tech's Vivek Sarkar, and that now is just the go-to register allocation in most of the industry compilers, because it does the job, and it is also very fast. But if you look at another technique called greedy, where it is based on graph algorithms like graph coloring, then it came from Chaitin and Briggs paper, and that is not something people use in industry, because it is, in the worst case, it takes exponential time, or not linear time when it comes to the allocation. There are heuristics and methods to minimize that time, but linear scan is something even LLVM does by default. Uh, this is just a pictorial representation of what I have explained so far. So, so I'll so now we talk about, let's talk about the involvement, right? I mean, okay, I have given you the theory, I have given you the glory details of LLVM and compilers, but where do I begin, right? So uh, um, getting involved in LLVM is not a difficult task, or what I would say is that being an open source project, it is hosted in GitHub. So GitHub is something that, if you know GitHub, and if you can relate to the LLVM projects or find the LLVM projects, then for you it is not a big deal to commit the patches, right? Because it is open source fundamentally, and there is enough support and the community available around LLVM which can help you to begin and help you to understand the code, and it is all just written in C and C++. So all you need is just understanding of C and C++, if you want to learn say implement your own pass or algorithm. I'm pretty sure that in your compiler courses you will be doing that. uh, but if you are coming from a non-compiler background, then it is not something like you you would feel that, okay, where do I begin or where do I start contributing. The open source project is pretty active, and it is just like the place where everybody contributes on a daily basis, right? To get started, you just start with getting started guide, and the discourse, there is a discourse channel where people discuss about the new thing, propose new things. There are ways to get your ideas noticed, and there are conferences also, like LLVM dev meetings, LLVM socials, where you can present your work and you can talk about the new ideas. You The LLVM dev meeting particularly happens two times in a year. One is in US and one is in Europe, and that is where it just happens like a normal usual conference, right? So I'll send these slides anyway after the presentation, but so you can get started somewhere, and also please feel free to ask questions, right? So now this is about LLVM. Now let us switch some gears and say talk about CUDA now. So there is a reason why I am talking about CUDA. So in the last slides, I will relate this LLVM and CUDA together, and then help you understand that the CUDA, which is the best standard or best platform for in today's world for NVIDIA GPU, how it is relating to LLVM, or how it is relating to compilers in general, right? So I'll be fast forwarding a bit in the interest of time, but the last slide I'll focus mostly on. Uh, so, uh, so CUDA, what is CUDA stands for Compute Unified Device Architecture. It is a one platform that NVIDIA offers you to program NVIDIA GPUs, right? I mean, now interestingly, it also came from an intern project at NVIDIA. Ian Buck was intern at NVIDIA, I think around 2006 or 7. Before that, it was just shader languages and shader assembly to program the GPUs. But CUDA as a platform, when it started, it gave you a C or C++ kind of interface to the GPU, right? Now, of course, at that point, it was very mature, but over the time, it has become so mature that it doesn't matter to you, or as a developer, it doesn't feel to you that, okay, you're targeting a CPU or you're targeting a GPU. The language feels exactly the same, right? So, so ultimately, what CUDA offers you is that same unified interface to your hardware. That is what any application developer or any software developer would want. That is the ultimate aim of CUDA platform. Now, inside that platform, we have different compilers, which is what we are interested in for this talk. There are developer tools, libraries, and of course the documentation. Now, libraries means, so if you relate from the CPU side, then you have libraries for doing your divisions, your libraries for doing your transcendental functions like the trigonometric functions, or you have libraries for doing uh, I mean, anything that's something you can't do yourself, right? I mean, for example, if you want to do a complicated computation for your program, then it may be available as a library for you. Similar concept is also taken to the GPU world, where the GPU libraries also exist, and as a programmer, you can just call into that. So that also comes under the CUDA platform, right? So GPU after all, it's a co-processor. It is not something this trying to replace CPU, because it doesn't have its own operating system, or it doesn't have its own Linux, right? I mean, there is nothing called as Linux on GPU. There is a resource manager there which helps you to talk to GPU, CPU. But after all, CPU and GPU are two guys live together peacefully in a one box, where GPU just helps you to accelerate your complicated stuff, and CPU just calls that big guy to help you to accelerate your application. There can be scenarios where you don't have to call GPU, right? Because it's a specialized processor. It's a graphics processing unit, which specializes in processing graphics related workloads. But over the time, it has become so mature that it is also capable of handling your complicated or compute intensive applications. Uh, uh, so we will go. I have talked about how it offers a unified interface to your hardware. Now, when it comes to language, what else can be more familiar than C or C++, right? Because it's been there for long. So CUDA's most preferred way of doing programming is C and C++. But the way you program is that you don't take the existing standard and write that. For of course, for the GPU, you have to tune that and add more language constructs in that, so that you will be able to target, right? So uh, there is a long detailed documentation which I can't cover in this talk, but here is a small hello world program, uh, where what we are trying to do is just take a small computation and put it on GPU, right? And that small computation is known as kernel. It's a function which we are aiming to call on the GPU, and the main is our usual standard main, right? So from main we call that computation, we call that kernel, and under certain configuration. So if you look at this 1 comma 1 after int main line, then you just say that I want to launch one grid and one group of threads in that for that particular current computation, and just execute that, right? Of course, there are different ways in organizing, and when it comes to configuration, we have different mechanisms to launch particular kernel on that. But this is a since this is a hello world program, we just start with that, right? And then the computation doesn't have anything in my program, because I didn't want to have a complicated computation and distract from that. But even if you have this third line, which is a printf, even if you copy paste that line to the kernel, it will still do that, what because what we are doing is that you take this computation and put it on GPU and say that. But if the computation itself is a printf, then it will just do the printf, right? And if you launch it with 100 different threads, it will say 100 different times hello world, because each computation or each thread is going to do the same thing, right? So I have given links to it there. There you can just read that, and there can be actually the CUDA introduction to CUDA can be separate topic for an hour. So I will not go deep inside that, because our focus is on compilers. So in the CUDA stack, then the most interesting thing is NVCC, which is now again. Let's come back to GCC and GCC and Clang. On the CUDA stack, we have something called as NVCC, which will be your go-to compiler for compiling the CUDA language or CUDA programs. And then it acts as a driver. It takes the program, it helps you to get the binary, and which eventually launch on the GPU. And it also comes with the tools like assembler and linker. So that is something. NVCC is something that you will be using if you want to do. So now slowly we are talking about compilers, right? uh, so when you look at the ecosystem, there are three different ways: libraries, open ACC directives, and programming languages. Programming languages is a green area, what we are talking about. uh, Uh, NVCC is something that CUDA platform offers for C, C++ languages. But over the last decade, CUDA also has matured enough and also offers you the new languages like Python, or Fortran, OpenACC, and even the new functional languages like I think Haskell is in the place, and there are some developments happening around Haskell. So not just limited to C, C++, but also functional languages are also grabbing the attention. Uh, no, so this is a pictorial representation of NVCC internally, or the CUDA developments kit internally. If you look at the second bar here, which is NVIDIA C++ compiler, then internally mm, uh, given that it's a compiler for GPU, but the developers are going to invoke that compiler from for any CPU and GPU application, right? Because just you don't write just a GPU program. Yeah, if you look at our Hello World program, it had a code for the non-GPU side of the world too, right? So NVCC, if we are targeting or if you are invoking, then it has to also talk to the existing LLVM or existing GCC compiler the on the CPU side, right? So that is why you have a two partitions here, where on the right hand side you have a CPU host code, and then on the left hand side you have a device specific part, where we internally we lower it to the something called as a PTX, which is a parallel thread extensions. This is where now what I have explained in the previous slide, it's helpful. This is where we talk about the intermediate representation. The PTX is the intermediate representation for all the NVIDIA GPUs we care about. This is the common place where all we lower everything, and that is why I explained a lot about middle ends, right? So this is where, if you look at the entire NVCC compiler, this is where our middle end begins. This is where we start all the optimizations and doing all the things matter for the particular hardware or particular architecture, right? But technically, if you can argue that okay, it doesn't look like a middle, it doesn't look like an intermediate representation, or it is very architecture specific. But in industry, the that notion of notion of language, or the notion of true intermediate representation doesn't hold. There will always be the cracks, and there will always be the hacks which people take. So it is not directly as we can compare it with LLVM IR per se, but this is where the interesting stuff begin. Uh, so this is a detailed example of doing a SAX PY. So I'll skip that. I think we have 6 to 8 minutes, and I also want to take Q&A. So I'll focus most of my time on this slide, right? Because this is where it all converges, what the CUDA and compiler. So this is an internal trajectory of NVCC, um, and this is taken from public places. So here is a link which you can just read. There is a detailed description about it, but this picture will help you to understand how the typical CUDA program is compiled in CUDA compiler. So mm, uh, starting from the top, the .cu is basically say your program like .c or .cpp. uh, and I told you that this is the CU program will have a host program, a host code, as well as a device code, right? So NVCC, it will split that code into the host side on the left hand side. Eventually, the bottom box is a C++ compiler. This is where your LLVM and GCC compilers will come. But on the right hand side, it will do all this. The green box which shows it does all the proprietary compilation. So as I explained, the .ptx file, eventually compile the device code into the .ptx, and the ptx as is nothing but assembler. If you have ever used assemblers, uh, then you might have heard of GNU assembler or GAS or LLVM assembler, LLVM-AS. This PTX AS is an equivalent to this in some world, not one to one, but in some world. So its job is to compile or take this .ptx file to .cubin, where is nothing but our ELF. ELF, again, that might be a new term, but there is something which you can which is ready to launch on the architecture or on the device. And then eventually these two paths get converged by the linker, and linker generates you the .o or the .obj files, which gets passed to the host linker, like our LLD or LD or any host based compiler you have, host based linker you have, to get the final executable, which eventually you can just do ./a.out, and then it does all the job, right? So what I'm trying to explain you is that what we have gone through in the slide is LLVM and middle lane and backend. So this particular slide just combines everything in the CUDA world, right? I mean, in the industry, where do we use the middle lane? Where do you use the backend and all that? So backend, if I say, then these PTX AS or these C++ compilers, all these guys have backend inside that. But overall, it arranged itself in such a stacked manner that all things come together and eventually you get the executable, and it all based on a fundamental compiler technologies that we learned in books. So this is where it we can apply all the learnings and all the things in the industry, because all I wanted to talk about is LLVM and industry, or the compilers and industry, and this is where it all is applicable to how compilers are the core feature of the CUDA stack, or how it is a bread and butter for the CUDA world, because it is all helping you to get your simple program to the executable, and and without this you can't even just explore the possibility of all the GPU compilation. Uh, yeah. So I'll just summarize or give you the broader picture, because CUDA is not just about one compiler. It is, as I said, it is an ecosystem of libraries, tools, and languages, and different things which come on build that, right, on which builds on top of the core functionality, right? Uh, and over the time, it has not just limited to the traditional applications like HPC or your weather simulation or physics based application. Machine learning and AI, has you must have heard of, or you must be definitely following how AI's adoption is increasing in today's world, and that is also where CUDA comes in place. That is why uh, the core stack has become more important than ever, because now, rather than just taking one particular application or one particular domain, the stack needs to be scalable enough to handle multiple domains, right? And similarly, CUDA as an ecosystem also invested huge in AI applications and AI libraries. So to develop a new model or to develop a new LLM, you don't want to do it from scratch. So as a ecosystem, it also offers you the multiple things. But after all, it all boils down to how the compilation or how the compilers happen. And recently, there is also a push on CPU side of the world, because that is where I am currently engaging in as a professional engagement. Grace CPU is something that NVIDIA is aiming to produce by the next year, which is based on ARM platforms, and I have links to that, so you can read about that. So I won't go into the deep every product of NVIDIA, but on this slide, what I wanted to focus is the stack, right? I mean, It doesn't limit itself to compiler, but your foundation is compiler. Based on that foundation, everything is built. You can't compile a library if your compiler is not up. You can't ship a new chip if your compiler is not up, because if you want to ship a new chip, your compiler needs to prove that okay, whatever you want to compile is fine on the new architecture, right? You don't want to ship that particular product to the customer unless there is a confidence internally, or unless you can prove yourself that I can compile to that, right? So compiler also comes into the life cycle of your product very early, so that it gives enough confidence for the further ecosystem to start their work. So again, we are talking about how these things, two things converge. uh, yeah, and this is my last slides. I hope I'm on time. uh, so if this enough generates enough interest to you, just and we are looking for new graduates, and you're looking for new people in this domain, or in general, any if you are interested in, if you got interest in libraries, if you got interest in non-compiler based things, then you definitely have openings. So please shoot me an email, and just feel free to talk, right? I mean, I'm not here to hire, or I'm not here to advise about NVIDIA openings, but my main intention is that system software engineers is not a old thing. There is enough interest in the industry, and there is enough things to do in the industry, right? I mean, with the advent of AI ML, this is this is just the beginning of era, and we are just pivoting, is what I would say. So if you are a system software engine system software guy, or want to go into that field, then NVIDIA can be a one option for you. uh, and here are the references. So yeah, that's all from my side. I hope it was interesting. So please feel free to ask questions, Rupesh. Do we have time to take questions, or
Yeah, we can
yeah,
take a few questions.
yeah.
Anybody wants to ask any question, please feel free. Yeah, Pranav, go ahead.
Sir, my question basically is that when you perform optimizations for CPU and GPU, right, in when you design a compiler, how will those optimizations be different? As in, can the LLVM middle end optimizations be directly ported for CUDA
Yeah,
compilers?
yeah. Well, LLVM directly we already use, but the way we represent the programs and the way we do optimizations are fundamentally different, because the architecture is itself different, right? So if you are aware from for about CUDA, then you know that you must be knowing that uh, on the CPU side you have one thread doing the computation, but on the GPU side you have more than one thread. Like, I mean, it can be even a million of threads doing the same computation. So when it comes to optimization, what we do is that we don't want every thread to do the same computation. We say that one thread does the computation, and then others just use it for their own purpose. So that is where the GPU centric part of the optimization comes. And if you're talking about LLVM per se, then already such kind of optimizations we do internally, uh, but not from an end thread perspective, but considering that the end threads are going to execute this particular program, so what can be useful, right? So that aspect is already there, built in the existing compilers to do that optimization. So does that clarify?
Yes, sir. Thank you, sir.
Anybody else has any question? Yeah, Gaurav. Go.
Hey, hi, Madhur. So I have one question. So, like, what is the basic difference between this LLVM and the JVM JDK architecture? Like, because this JVM JDK also does a similar kind of thing, right? Like, first we have a bytecode, and then
Yeah.
that bytecode gets
Mm,
converted into
mm,
like based on the architecture. So,
mm.
like, how they are different.
Now, well, in terms of different, it's a different technology. I mean, JVM aims to compile Java-based programs. LLVM is there, not there yet. I mean, there can be some projects which try to compile Java programs to eventually the machine code, but fundamentally or historically this has been a separate technologies to do that, right? So because Java comes from Oracle, and they had their own technology and the translation mechanism to do that, and then LLVM came. But if you ask me, and then fundamentally they must be doing the same transformation. It is just a different implementation, in my opinion.
Sure. Thanks.
Yeah, Chinmay, go ahead.
Hey Madhur, so recently I've been reading there has been a lot of interest on MLIR, I think, which builds on top of LLVM, right?
You're right. Yeah.
So are there any projects at NVIDIA where MLIR is being used or is being
Yes.
worked upon?
Yes. Lot of projects. So in fact, uh, so what MLIR is is like the next big guy at NVIDIA, or machine learning based optimization or machine learning based techniques to do the compilation is the next big guy. Uh, but like I mean, you can relate it to the AI applications that NVIDIA compiles, right? Or the AI based architectures, the Ampere or the Hopper that you must have heard of from NVIDIA. Eventually that goes through a MLIR or at some point, and some compiler uses that internally. So you can just browse that, you can find that details. But yes, there are a lot of things around MLIR.
Okay, thank you.
Okay, any final questions? All right. If not, then let me thank Madhur on behalf of all of us for spending time with us and giving us a lot of information related to both compilers as well as how it gets used inside the CUDA uh, compilation chain. Um, so thanks a lot, Madhur, for your time. And
Thank you.
I'll be ensuring that this recording is posted on the Alum at Alma webpage.
Thank
Thank
you.
you, everyone, for joining.
Thank you, guys. Please feel free to talk and feel free to shoot your mails. I'm available. So my email ID will be shared there. So just feel free to talk. Thank you.